Hi, this is my video number 22. Right, I'll talk on the Hilbert-schmidt solution of non-homogeneous Freedom integral equation of the second kind. Yeah, Hilbert-schmidt SCMIDT solution for non-homogeneous Freedom integral equation of the second kind. Okay, Hilbert-schmidt solution for non-homogeneous Freedom integral equation of the second kind. Alright, so first we consider the non-homogeneous Freedom integral equation. Consider the non-homogeneous Freedom integral equation. Freedom integral equation of the second kind. Which is given by ux equal to fx plus lambda integrate a to b k xt ut dt. Okay, let's call this equation number 1, where k is continuous, real and symmetric. Okay. K xt continuous, real and symmetric, and lambda is not an eigenvalue, not an eigenvalue. So this equation here you can write as a rewrite those equation 1 as a ux minus fx equal to lambda a to b kxt ut dt. Okay, so just we bring f to the left side, and by the Hilbert-schmidt theorem you can write this as a multiplication of some coefficient with a normalized eigenfunction, yeah, using Hilbert-schmidt theorem that I've given in the previous lecture, yeah, by Hilbert-schmidt theorem. We have this part here as you can write as a ux minus fx equal to, that one is a summation of am phi m x, yeah, m from 1 to infinity, and a between x between a and b, x a and b, where your phi m here, where phi mx for all m 1, 2 and so on are the normalized eigenfunction, yeah, normalized eigenfunction for this homogeneous Freedom integral equation. We have ux equal to lambda a to b k xt ut dt. Okay. We have explained this, how to find the normalized eigenfunction and so on and so forth. You just follow those things. And then so let's call this equation, I call this this is number 2, this equation number 3, okay, and this equation I call it number 4, so to make us easy to refer later on. And we let lambda m, where m 1, 2, and so on, be the corresponding eigenvalues for the homogeneous Freedom integral equation. Yeah, let that be the corresponding eigenvalues of homogeneous Freedom integral equation. And also we let lambda different than lambda m for all m. Okay. For all m. Let's call this condition equation number 5. And since phi m are normalized eigenfunction, since phi mx, yeah, for all m are normalized eigenfunction, we have integrate a to b phi mx and phi nx dx. This one is either you have 0 or 1 for m different than n, and for m equal to n. So let's call this I think I give a name number 6, this one. Alright, then if you multiply equation number 3 here with phi m, and we integrate over x from a to b, what we have, so we multiply 3 with by phi mx, right, and then we integrate from a to b with respect to x. So what we have is that for this we multiply by phi m and integrate. So for first term there we have integrate a to b ux phi mx dx. The second term there you have integrate a to b fx phi mx dx. And then on the right hand side, if you split that one by one, term by term, so that give you, we have a1 integrate a to b, we have phi 1 x phi mx dx, and we have phi 2 and so on up to m terms. Yeah, am integrate a to b phi mx dx and so on. Then if we define Cm as a integrate a to b from there as a ux phi mx dx, and fm as integrate a to b ux phi m fx here, x dx, and we use the normalized relation of the eigenfunction, this one here. You can see if, for m different than m n, that gives you 0 and the rest. So which means we have this part is 0, this part is 0, this part is 0, what left is only that. Okay, so what we have, I think I'll give a name, easy for me. I give a name here. Let's call this number 7, let's call this number 8, let's call this number 9. Okay, and then from 6, then from equation 6, this equation here, this equation, the relation between the normalized eigenfunction and 7 here, okay, 7, and also 8 and 9, 8 and 9. So what we have is that Cm, because this one is we define as a Cm, this one we define as a Fm, so we have Cm minus Fm. This is equal to, on the right side you have 0 everywhere except this one. This is equal to 1 by using normalized eigenfunction. Then we only have plus Am, equal to Am. Right? So let's call this equation number 10. Now if we apply, multiply equation 1, the equation 1 is the non-homogeneous Freedom integral equation here. This is equation 1. We multiply equation 1 by phi m, both sides of course, phi mx, and we integrate from a to b, whatever inside there, with respect to x. So what we have, integrate a to b ux phi mx dx. Okay, and on the right side we have integrate a to b fx phi mx dx, plus we have lambda integrate a to b kxt ut dt dx. Okay, and using the definition 8 and 9, using 8 and 9, so what we have, this is our Cm, that gives us Cm is equal to Fm plus, and also the fact that K is symmetric, you can change the order of integration, using the fact that K is symmetric and K symmetric. So we can write this as a Fm plus, we have lambda there, then integrate a to b, we just take out ut, change order of integration. The inside, let's become integrate a to b k tx, due to the k is symmetric, we have phi mx dx dt. Now, since phi m are the eigenfunction corresponding to the eigenvalues lambda n of the homogeneous Freedom integral equation, since phi mx are the eigenfunction which is corresponding to eigenvalues corresponding to the eigenvalues lambda m of equation number 4 here, the homogeneous Fredholm integral equation, number 4 of 4. So we have phi m x is equal to lambda m integrate a to b k x t phi m t dt. Okay, and then you can write this as that one just the same as change the variable a to b k xz phi m z dz. You just change the variable, just the same thing. Or this is, you can also write as a lambda m integrate a to b k is symmetric, so k x tx phi m x dx. Yeah, you just change the variable. You can see that from t, then we change to z, then we change to x. The reason we do this is just to try to avoid the confusion, because here we have x and t, and here we have t and x. So we just try to avoid the confusion. And the purpose of doing this is that we try to substitute the terms inside that curly brackets. Okay, so from this relation here, let's call this equation number 11. Okay, from this relation here, what we have is that integrate a to b k tx phi m x dx. This is equal to phi m t over lambda m. Okay, so we substitute this value. So let's call this equation number 12. We have 11, we have 12 now. Okay, so if you substitute this equation into the previous equation number 11 here, yeah, because this is the we want to substitute that everything in the curly brackets. Then we substitute 12 into 11. So we have Cm is equal to Fm plus we have lambda integrate a to b, then we have ut, then everything in the bracket is phi m over those things, so phi m t over lambda m dt. Okay, then you can rewrite this lambda m, you can take out, so that give you phi m plus lambda over lambda m integrate a to b ut phi m t dt. Okay, and ut phi m, I think we have defined from 8. Yeah, this equation number 8 here, that we define as Cm. Then using 8, we have Cm is equal to Fm plus lambda Cm over lambda m. So let's call this equation number 13. Alright, and then from equation number 10, from that equation number 10, we can write this Cm as Am plus Fm. Yeah? From 10, we have Cm is equal to Am plus Fm. Then if you substitute into those equation 13 here, then from 13 we have Cm is given as that, so we have Am plus Fm, that's equal to Fm plus lambda over lambda m and Am plus Fm. Okay, then you can simplify this thing. That gives you take out Am, you have 1 minus lambda over lambda m. This equal to, you bring those Fm to the right, so basically that one is cancelled out. So what left is lambda over lambda m Fm. Okay, and then you can write, therefore we have Am is just lambda Fm over lambda m minus lambda, for lambda m different than lambda. This is let's call this equation number 40. Then if you substitute this value into our equation number 3, alright, this equation here, where we have found Am. Now the purpose that all we have done is to try to find Am. Once we have found Am here, we just substitute into that equation. So then we have substitute Am into 3. So we got Ux is equal to Fx plus lambda summation m from 1 to infinity. We have Fm phi mx over lambda m minus lambda. So let's call this equation number 15. Again, from equation number 9, we have from 9, which is Fm is equal to integrate a to b ft phi m t dt. The difference with 9 is that we change the variable of integration. Okay, and then from that we can substitute this Fm with everything here. Okay, then from 15 we have Ux is equal to Fx plus lambda summation m 1 to infinity. We have phi m x, we have lambda m minus lambda, and Fm we substitute with those. We got integrate a to b ft phi m dt. Then interchange the order of summation and integration. That I can write this is equal to, we have fx okay, from that we have fx plus lambda integrate a to b summation of, so that we change order of integration and summation. We have m from 1 to infinity, so that here we have phi m x phi m t over lambda m minus lambda, that one is everything there. So we have ft dt. So that we can write this as a fx plus lambda integrate a to b, that's as a rx t lambda f t dt. Yeah, where we have defined r x t lambda as summation of phi m x phi m t over lambda m minus lambda. Now from here we have the possibility of three possibilities, where we might have a unique solution, we might have no solution, and we might have infinitely many solutions. So you can see here the solution is obtained here. This is ux equal to everything. So if lambda m different than lambda, so then we obtain a unique solution. Yeah, if lambda m equal to lambda, then we might have either infinitely many solution or no solution. So let's see those things. Okay, so let's consider this as a case 1. Yeah, case 1. We have a unique solution. So if the condition lambda equal to lambda m different than lambda m is satisfied, then we can see from equation 14, then from 14, which is am lambda fm equal to lambda m minus lambda. So it is obvious from here, if lambda m different than lambda, then we can find what am is. Yeah, we can find what am. So if lambda different than lambda n, then from 14 we can find am. Alright, of course in this case it's a unique. Then if you substitute, yeah, and putting the value am, into our equation number 3, that equation here, because that gives you a solution. Alright, and then into 3, that will lead us, we obtain the solution, which is given by solution of 1, which is given by equation number, let me see, equation number 15, that one. Yeah, equation number given by 15, which given by 15, which is unique. Okay, provided that this equation satisfied. Now, the second case is that we have no solution. No solution. So for this case, if we consider lambda k be the case eigenvalue, and then we let lambda equal to lambda k, alright, and fk is different than 0, which is to say that the eigenvalue, the eigenfunction, which is the eigenfunction phi k x is not orthogonal to fx. Yeah, is not orthogonal to fx. So in this case, we will find there exists no solution. Yeah, so we have exists no solution. Exists no solution. Since we can see from that is that fk phi k lambda k minus k, because since that one is vanished, this is undefined, so this thing is not defined. It's not defined. Okay, and the third case, case number 3, case 3, we have infinitely many solutions. Infinitely many solutions. So if we let lambda equal to lambda k, where k is the kth eigenvalue, the same with this eigenvalue, and we let n, and we have fk, this is equal to 0, which is to say that the eigenvalue, the eigenfunction, that the eigenfunction phi kx is orthogonal to fx, is orthogonal to fx. So in this case, we have for m equal to k, then equation number 13, yeah, equation number 13 is this equation here. All right, we'll give, then equation 13 give, we have a cm equal to that one, fm is 0, plus we have lambda equal to lambda m, lambda over lambda, then ck, yeah, this is ck, then which give from here ck equal to ck. What does it mean is that we have no restriction on ck, which means you can put any number of ck, then that gives you a infinitely many solution. Yeah, that gives us infinitely many solution. many solution. And therefore, the equation solution number 16, where is 16? Cannot find that one. The solution number 16, which is Fm, is given to here. Where is it? I cannot find that one. Oh, here. This one here. This is 16. Okay. So therefore, in this case, the solution 16, I think not 16. This shouldn't be 16. Where is it? Just a minute. Okay. Therefore, the solution not 16 should be 15. Yes, 15 can be written as we have ux is equal to fx plus a 5kx plus lambda summation fm phi m x, of course, for all m over lambda m minus lambda, where a is any constant, and m equal to k. So therefore we have infinitely many solutions. Okay, so I described how do we use the Hilbert-schmidt solution to find the solution of the non-homogeneous Fredholm integrate equation of the second kind. The step is quite straightforward, even though it's a little bit lot of work to do, but it's still considered quite straightforward. So next is that I will give you some example. All right, but not in the video. In the next video, I'll give the example on how to use this approach. All right, so for this video, I think I'll stop here until meet again in the next video. Bye.